It's my pleasure to introduce Vittorio, or Vit, who is known for his open source work and 3D printing and maker technologies as part of science, and especially in the context of chemistry. So what we have in common is that we both work a lot with microfluidics. Of course, the LIBREhub is also focused a lot on optics in general, microscopy. So there is definitely an overlap. But today we'll mostly be talking about microfluidics and how to use open hardware for microfluidics research. So thank you very much for taking the time to share some of your many exciting projects with us, Whit.
Thanks a lot for inviting me. It's very nice to even virtually be here anyway. I'm Vittorio Saggiomo, as Tobias say. I'm from the laboratory of BioNanoTechnology in Wageningen, which is a very small city, but it's nicely because it's in the center of the Netherlands. So in 1 hour, you can reach practically all the Netherlands almost by bike. Today I'm talking about open hardware microfluidics, and I will start always on why I'm doing what I'm doing. And my point when I start doing research is that, okay, we have a lot of problems that we want to solve. This one are the UN sustainable goals that we want to achieve in 2030. And each one of those problems has a subset of problems, and we need to solve most of them by 2030. Who is going to solve those problems? So I start doing research, or I start doing chemistry to improve the world. Maybe it's too much, but to do a job, leaving the world a better place than when I started doing research. So if I do this, okay, let's say researchers are going to solve those problems, or at least are tackling this problem, but where are those researchers, or how many researchers are actually actively working on those? And if you see this map, the amount of researcher is not that nice, because hypothetically we can do way better for solving this problem, and we are losing a lot of brain power just because not everyone is, let's say, allowed to do science. And one of the problem here that we saw is the lack of open science and reproducibility and open hardware and all of those, mostly on open science part. If you hear talk about open science, many people start talking about open access, which is a very important point, but it's not the only point. So if you are able to read a paper, it doesn't mean that you are allowed to reproduce it. So for example, if you're using MATLAB, or if you're using some other very expensive program, it's very difficult someone can buy those programs or the license for those programs. So there is another level of open science, which actually it's open technology or frugal science. This is Manu Prakash. It's one, probably the leader in frugal science in the world. But also you have open hardware. So for example, you have also companies that are actually only focused on open hardware. So for example, Prusa or Arduino, so that you can really reproduce the hardware itself. This is why I'm doing, but what I'm doing and why I'm doing microfluidics. I like microfluidics because you can do a lot of things with microfluidics. So I don't like to work always on the same field. And I thought, okay, if I'm doing microfluidics, I can jump from one project to another, and I keep my brain occupied in doing multiple different things. So my background is in chemistry, but I can also collaborate with a lot of people from the physics part. We have paper on organ on a chip because we collaborate with people on organ on a chip. We do separation, we do analytical chemistry. With doing microfluidics, we can do a lot of different things and collaborate actually with a lot of different people from different backgrounds, which I always think it's very interesting. So what do I need to have a bench which is dedicated to microfluidics and which fully based on open science? So I need the syringe pumps for driving my liquid, I need a microfluidic device, and I need hopefully a microscope for looking what's happening on the microfluidic device. So we start almost 10 years ago tackling the microfluidic device, because at that time we were still doing replica molding fabrication, which is an amazing way of doing microfluidics. Was invented by Whiteside 20, 30 years ago, in which you have a layer, could be glass, could be a silicon wafer. You put a photoresist, you etch or cure photoresist for having your positive mold. You put PDMS, which is this transparent material elastomer. You cure it, you remove it, you attach it on top of glass, either using plasma or piranha technology. And then you have your mixed microfluidics, which is part of glass and part of this PDMS material. It works wonderfully. There are different problems here. It's mostly bidimensional because you have only 2 dimensions if you're doing this method, or you need to put multiple layers of PDMS on top. You need a harsh chemical, either a piranha solution, or you need a plasma oven. Delamination is possible. So when you have too much pressure, you may remove the PDMS from top of the glass. And in general, with a 3D printer, you can print ABS, which is one of the standard material for 3D printing. You put it in a beaker, you throw some PDMS in it, you cure it, and then you throw everything in acetone. What happens is that the acetone will dissolve the ABS, but not the PDMS. So you start from a wire that it's this ABS wire, and at the end you have a single material, which is PDMS, and you have a 3-dimensional channel inside that. We can make very complex devices. We can make material that doesn't have any glass in it, so it's practically indestructible. And we can also make devices with different width in there. So one of that is with 500 microns, but also with a channel of 90 microns. You can use a 3D printer, so you can make whatever shape you want. So this one, for example, is 1.5 meter, just because it was printed. So you make a channel in a channel. You can print practically wherever you want, and then you just dissolve it and have your channel in the PDMS. You can make something called ship in a bottle. So it's where something it's bigger than the inlet and the outlet. So here we print a chamber. We put either a steering bar on the top picture or the amber light catalyst in the bottom picture. Then we dissolve, and the material that it's in this chamber is bigger than the inlet and the outlet. So it's actually stuck in there. So you can use for mixing those 2 colors, or also for making catalysis and flow. Again, it's pressure resistant because you don't have glass anymore. So the failure point, it's in the inlet and the outlet with your tubing, but it's very difficult to break the PDMS itself. And we can make also selective heating. So it's not very, cannot conduct temperature very well. So you can use this wire near a specific point in the channel, and you can reach 300 degrees in a few seconds just if you apply some current on it. We can make something also very fancy, which is the NMR on chip. This is something that usually costs around 10,000 euro. We did it for €1, achieving similar results. We can also embed all the electronics that we want, because again, PDMS is not conductive. So we can throw the full Arduino there, colorimetric sensor, everything is embedded in PDMS, and everything can work directly on top of the microfluidic device. So this was the first part. Okay, fair enough. Many people actually start using this method, and those are people that have never seen or have never done microfluidic in their life. So those on the left side are real doctor, and on the right side are biologists. They have never seen or never experienced how to make microfabrication, microfluidics, and they were also able to use this method for using microfluidics in their own lab. So in the microfluidic device, that's very easy. This method, you can literally do it at home, because ABS you can buy wherever 3D printing shop. Acetone you can buy in, again, wherever shop you want, because it's just nail polish. And also the PDMS you can practically buy from Amazon. Then we need a syringe pump. So now we have a microfluidic device. Let's talk about syringe pumps. If you are in any microfluidic laboratory, or in fluidic laboratory in general, you probably have worked with one of those pumps. So this one costs around 800 euro. It push only syringe, so you cannot withdraw liquid. It has a serial port. It works still on Windows 95. If you want to pre-program, it's very expensive and very difficult to make it programmable. So I cannot leave this pump running overnight, making whatever I want. So that's impossible. On the other hand, I love 3D printer. So for the same price of one syringe pump, I can actually buy 6 3D printer. This doesn't help me because I want a syringe pump, but usually I start comparing price with 3D printers. So I can buy 6 of them, but maybe I can also use them. So if you look around the literature, there are quite a lot of amazing do-it-yourself syringe pumps. So the one, for example, on the left, it's the Poseidon, a pump system that I really love. But I have a problem with all of those builds. So you need to look for the different electronics, which most of the time coming from AliExpress. And there are different vendors. So the electronic itself may be a little bit different. You need to find different shop also for all the mechanical part. So sometimes it's a treasure hunt. Many times you need also to solder, to tune the motor, and to also probably sometimes doing the software yourself. So the software it's available, but in many cases, especially if you're going on Python, the libraries may be in conflict with some other libraries that you have on your computer, and it's difficult for a person that have never soldered or never done method or something like this. So we went back to the original 3D printer, which is this Creality Ender 3. I'm talking about this one because at that time, so 2 or 3 years ago, was the cheapest that you can buy. It was still quite good, but most importantly was open hardware and open software. So open hardware, you can find all the schematic on GitHub, and open source because Marlin as firmware on the board has always been open. So you get the box. The box, instead of building the 3D printer, you actually just open the box and see what is inside. So you actually destroy the printer, and you can find a lot of things inside the box. So you find the linear rails for motors, fan, motherboard already with the firmware already fresh. You find the power supply, LCD if you want to use the LCD, heating block with the thermistor. You have the screw, and you even have the hex key screwdriver for building it. So our idea was, can we use everything that is in this box for building a 3D printer? In this way, we don't need practically anything else. We just need to buy this box, and we build some syringe pumps. And this is actually what we did. So all the rods and the movement and the motor and the linear part are coming from the 3D printer. So all the electronics and the mechanical part are coming from the 3D printer box. Some pieces you need to 3D print, so before destroying the 3D print, you should print those pieces. And the only 2 things that you need to buy is this long screw and the coupler from the motor to the screw. Those are the only 2 things that you need to buy out of Amazon or practically any other shop with mechanical part. So now with €150, you can buy, you can build 4 pumps. Most importantly, you also have the motherboard with Merlin already embedded in it. So you can use G-code for working those syringe pumps. So now if I say G-code, G1 means move, X means the motor X, 10 means 10 millimeter, and F0.1, it's the speed. So now you have this one, you can pre-program, you can put the SD card on the driver board, and it will run overnight, making different variation of the pumps. So again, for the same price of a single non-programmable syringe pump, now you can have 24 pumps that are completely programmable. Open hardware also means building instruction. So once we did the research, which probably was the fastest thing, building instruction takes a huge amount of time. But we have a build guide, which is picture by picture, each single step that you need to take. And this was done by Sander, who was a PhD in our laboratory. These take usually a huge amount of time. We also have a GitHub and also YouTube video on explaining not only how to build it, but also how it works, the principle, the transformation between circular movement to linear movement, and all of those small things. Even before we publish, we put it on GitHub, we put everything on a preprint, and people already reproduce it. And this is the things that we want to usually see if you are doing a project like that. So we want people to confirm that build works and the pump works, and some people even start modifying it. So the one on top right were already something changing from our own design. We are also trying to do live publication. So when something happens that we want to do something a little bit more or new experiment, we cannot publish another paper, but we still think that there is something interesting to say to the people that are reading this paper. So we are using PubPeer like addition to this this research. And this one, for example, it's an addition from Maiwen, the laboratory of Maiwen, which she did an experiment checking how good is this pump compared to the classical red one in terms of vibration or pressure oscillation, and they are quite similar. We are keep adding things. So, for example, we got a question of, okay, can we drive two syringe on a single pump? So we redesign one block, and now you can still download it from GitHub, even if it was not in the first publication. And we are using also a lot of solving issues there, because sometimes there are problems with the pumps or the computer or with software, and instead of replying one by one with the emails to the people that are finding those mistakes, we just write an issue there, we solve it, and we can say, okay, just go there and check if the problem has been already solved. This was one of the first time that we did something with the 3D printer. At that point, say, okay, don't look at the 3D printer as a 3D printer, but look at the 3D printer as a cheap, very cheap robot that you can use in a laboratory setting. And that actually sparkled the idea of making multiple things with those printer. So this one, for example, is a histology machine. So you have the glass slides, and the glass slides are moved from one vat to another for making histology easier and automated. This one from Felix from Munich, it's similar, but it's a deep coating machine, and they use actually the extruder motor for pinching a single slide and for moving the slide from one vat to another. But we also have now an endoscope, which the microscope can be both in reflection and in fluorescence, and it can move in this 20 by 20 centimeter space. But also, for example, this ARA printer, which is an Arabidopsis printer, so we pick up one single seed and put it in agarose in a very reproducible way. Fine, we have syringe pump, microfluidic device, and then we tackle the last point, which is having a good microscope. And if you think about good microscopes that are 3D printable, do it yourself, obviously the first one you should come in your mind, it's the Open Flexor from Richard, actually a lot of people, and from Bath, the first one, but also the UC2 from Benedict. Those are very nice systems that you can have in the laboratory. But 1 year ago, we were looking for something that can be brought in field, because we had this microfluidic device in which you have a staircase inside, so it's a microparticle sorter. So if I flow particles, they are stuck in this microfluidics depending on their size. So if we have 25 micrometer or more, they will be stuck in different part of the microfluidics. And we were using this specific microfluidics device for detecting the schistosoma eggs, which is a parasite. It's found in urine if you have this parasite. So the thing that they usually do is actually checking the urine for those eggs. So if you are passing now the urine in this microfluidics, the egg will be captured there, and we need to find a way to look for that. With the same microfluidics, we can also check for zooplankton, for checking how good the water in your river is, or for microplastics. So nor the Open Flexor or the UC2 are really portable. So they are portable, but not in the way that we were looking for. So how to visualize those microparticles in field. And for doing that, I contact Benedict, which is one of the inventor actually of the UC2. And together we devised this very small microscope, which is still a compound microscope, works on the ESP32. It has magnetic Z for if you want to put the slides up or down. And you still can get a resolution between 5 and 10 microns. So you can still see those eggs with this very little microscope that can fit in our pocket. It just needs a battery. It works on Wi-Fi, so you attach it on a power bank. It will make a Wi-Fi hotspot. You connect to that Wi-Fi, open a web page, and then you can control the microscope from there, taking picture, taking video, taking whatever you want. Those are just some mosquito. You can see tardigrade and rotifer there. It works extremely well. So again, before we publish, we put it on a preprint. We put all the details in there, and not even 10 days later, many people already replicated the design. They were happy. If you look on the small, how small it is, you can see also people putting it on top of dogs. And this is also what we did as well, just for checking how small it is and how good the dog it is for keeping it there. But that's another point. So we can do all those 30 things. Now you can have a bench with microfluidics, and everything there, it's open, from the pumps to the microfluidic device to the microscope. So what are we doing now? So what's the next part? This is still made or is still used by someone in the lab. And what we are trying to do here, it's actually using a computer for doing everything automatically. So we are going for using computer vision. You can see this is, for example, the setup. We have the pumps, we have a microscope, we have a microfluidic chip, and we have also a Raspberry Pi there that is controlling the loop. So we see a chemical reaction, and then we can act out of that. So for example, this one, it's a simple complexation reaction in which we are detecting iron, and then you can control the pump for having more of this complex or less of this complex. So everything from the microscope, you control back, or automatically the pumps are controlled back. And this is practically it. It means that you can do all of these things on a single bench, completely open. Also, what are you doing with computer vision? Obviously, will be completely open, and all the programming will be completely open. If you are a little bit more interested in the 3D printed part, there is this review that I wrote, I think, a couple of years ago, in which there is a part on how to use the 3D printer as a robot, which I think it's very interesting. And also for the price that you're buying those 3D printer, you cannot buy a robot that cheap. For microscope, we also wrote, or actually I helped in writing this other review. So this also it's quite interesting if you want to read something about 3D printing and 3D printing and robots or microscopes. And obviously, I need to tell that we are also having this journal open hardware, and recently we moved to Diamond Open Access, which means that no one is paying for the paper, not the reader, but also not the researcher. So if you want to send something that is for open hardware, you can send it to this journal, and no one is going to pay that. Last thing, because I think that was the main point, is that how to do open science. And you should always think about the audience. That's the first thing that I do, but I do most of the time methodology. So I know which audience I need to reach. And one of the simple things that you can do is actually simplify everything. If you want your method to be used, it should be as simple as possible. Open access, preprint and postprint should be the standard thing. This will require a little bit more effort. So how to write the experimental section step by step. If you want to make videos, the data should be fair if you are using data, if you are publishing data as well. Again, Tretoad, commercial software, you have no idea, or probably actually you do have how much console cost, how much MATLAB cost. Those things are insanely expensive. So if you can use something that it's not commercial, try to use Python. There are 100 million different library or program on Python. It's more than enough for doing most of the stuff we do. And obviously support your research. So once you finish publish your paper, it's not a dead end there, but keep that alive. So try to help people in using your research. I want to thank obviously the working group. We do not only the open science, for let's say chip technology, but we do also a lot of high-end technology. For example, with the NMR, we have also a very expensive NMR in our laboratory. We do a lot of chemistry, we do a lot of chemical synthesis, but also nanoparticle synthesis. We do a lot of different things in many different topics. And obviously, I want to thank you for inviting me. This time it's online. I hope that one of the next time I will be live there, which will be very nice. And thanks a lot.
Thank you very much. That was a great presentation. And yeah, thanks for putting so many different things in there as an overview to your different projects. I think the NMR is also very, very interesting to hear more about. And yeah, also another thanks for taking over as editor-in-chief in the Journal of Open Hardware. I think that was a really great push, and I'm really glad to see that project continued in good hands.